This is part 4 of the second lecture of week 9. And last time we discussed how we can find inverse Laplace transform of sum or difference of some fractions which has similar form to the form of the Laplace transform in the right column of the table. What if our function is not in this form? For example, if we want to find Laplace transform, inverse Laplace transform of this fraction, what can we do? And this fraction is not the same as the fraction in the right column table, but we can write the denominator like s, so just completing the square plus, and here we have 9, so 3 squared, like this. And numerator is different. It cannot be sine or cosine. It cannot be e to the at sine, e to the b cosine, because the numerators here are different. What can we do in this case? In this case, we use method of partial fractions. For example, in this particular example, the idea is to write it as a times the same denominator, and in numerator we choose the same, let's say b, like here, to find how many signs we'll have. So b is 3, so we write 3 here, plus b times, again here we ask how many cosines we'll have. So we numerated here s minus a, so the same as s plus 1 in our case. So, and we need to find the coefficients a and b to split this fraction into these two fractions. After we find a and b, we can say we have a times e to the at cosine bt plus b times e to the at sine bt. And method of partial fractions, it may have 3 types. The first one, non-repeated linear factors, second, repeated linear factors, and third, quadratic factors. So depending on what we have in the denominator. Let me consider the first case, the non-repeated linear factors. Non-repeated linear factors, this is the case when we have the function f of s is some polynomial of s over some linear factors, some product of linear factors which are different. So assume we have n linear factors in the denominator, and in this case we always can write this function as, say, some a1 over s minus r1 plus a2 s minus r2 plus so on, plus an over s minus rn, where we need to find these coefficients. An are numbers that we need to find. And after we rewrite our function f of s as the sum of these simple fractions, we can find the inverse Laplace transform at a point t. This will be a1, and you can see that in the table of inverse Laplace transform, s minus r1, this is e to the power r1 t, plus a2 e to the power r2t, plus so on, plus an e to the power rn t. So let me give you an example for this particular case of non-repeated linear factors. For example, our fs is a function given like this, and we need to write it as a over s plus 1 plus b over s plus 2 plus c over s minus 3. So we need to find these coefficients a, b, and c. And there are in fact two ways to do this. The first way to write a system, so the first method, to write a system of linear equations where unknowns are a, b, and c. How we do this? We find the common denominator summing these three fractions. Here the denominator for a is the product s plus 2 times s minus 3. If we open the brackets, we get s squared minus s minus 6. The multiple for b is the product s plus 1 times s minus 3. That is s squared minus 2s minus 3. The product for c is s plus 1 times s plus 2. So s squared plus 3s plus 2. And then we find the coefficients of s squared of s and s to the 0 and compare with the coefficients of f of s, 7s minus 1. So let's see what we have for s squared. If we multiply a times this thing, a times this thing, we obtain just one coefficient s squared, which is just a. The same for b times this bracket, b times s squared, so the coefficient of s squared is b, and the same for c. And since there are no coefficients, so no s squared here, we write it 0. S to the first power, this is when we multiply a, we got minus a, minus 2b, and plus 3c, and the coefficient of s for our function is 7, so this is equal to 7. For s to the 0, so the constant coefficient is minus 6a, minus 3b, plus 2c. And this one, the constant coefficient of our function is minus 1, so this sum is minus 1. Next, we solve this system. Let me just give you the the solution. So after solving this, we obtain a is equal to 2, b is equal to minus 3, and c is 1. So after that, we write f of s as 2 times 1 over s plus 1 minus 3 times 1 over s plus 2 plus 1 over s minus 3. And so the inverse Laplace transform of f at a point t is 2 times e. So we look at this line in the Laplace transform table. E to the power minus 1 times t, so minus t, minus 3 e to the power minus 2t, and plus e to the power 3t. So this is the inverse Laplace transform. There is also a second method how we can find this a, b, and c. What we do, we find the common denominator and multiply a, b, and c by the brackets that we need to add. So we write 7s minus 1 is equal to a times s plus 2 s minus 3 plus b times s plus 1 s minus 3 plus c times s plus 1 times s plus 2. So we obtain this expression like here. And now we just take different numbers for s, different values of s, and see what we have. S, to make it simple, we take s such that we make two brackets here to be 0 and one bracket is non-zero. So let's say s is minus 1. In this case, what do we obtain? The left hand side is minus 7 minus 1, so minus 8. And the right hand side is A times minus 1 plus 2 is 1. Minus 1 minus 3 is minus 4. So we immediately obtain A is equal to 2. Let's take S to be equal to minus 2. Then we get minus 2 times 7 minus 14 minus 1 minus 15 is equal to, and now the bracket for A is 0, the bracket for C is 0, and the bracket for B is minus 1 times minus 5. So B is immediately minus 15 divided by 5 is minus 3. And when N is, we take S to be 3, the third value. In this case, the bracket for A is 0, the coefficient of B is 0, and the coefficient of C is non-zero. So we substitute 3 in here. 3 times 7 is 21, minus 1 is 20, is equal to C times S plus 1, 4, times S plus 2, 5. 4 times 5 is 20, so C equals 1. So we immediately obtain the result here. A equals to B equal minus 3, C is 1, just by this simple way.